Just like that. 16 times.
Do we have to factor it?
Did you get 48x squared minus 12?
Yeah.
Yeah.
That is the correct answer. Perfect. 3 times 16 is 48. Subtract 1, you get 2. And the 7, what happens with the 7? It goes away. Okay.
Okay, William.
So let me tell you its limitations. Okay.
I can't wait.
You can only use the power rule when things are simplified. Okay. You can't use the power rule on fractions or products. But let's do it this, okay? Cannot. I'll put cannot here. On products, cannot use it on products. You cannot use it on quotients. There are separate rules for products and quotients, which we will learn in section 3. But I want you to know about it now so you can learn ways around it. Let me show you what I mean. Let's do something simple. Okay, so we cannot use the power rule when there's products or quotients. Let's say I have x plus 1 squared, and that's my h of x. Let me move this up so you can see a little bit better. Let's say I have x plus 1 quantity squared, and I was trying to use this power rule. I want to use something that's nice and simple. Well, you can't use the power rule for this particular problem. Why? Because it's a product. It's an x plus 1 times an x plus 1. Okay? So this is the same thing as x plus 1 times x plus 1, right? There will be a way to use this, but in section 4 we're going to learn the chain rule. So products, quotients, and maybe I should say groups of powers or something like that, because this one has a power to it, which is a bunch of products, right? So if I have x plus 1 times x plus 1, that's the same thing as x squared plus 2x plus 1. Isn't that the same thing as h of x? Now, do I have an x multiplied by another x? Up here, I have an x times an x. I have a product of variables. Do I have a product of variables here? Is this x squared being multiplied by another x? Is this x being multiplied by another x? No. So I can actually use the power rule here at this level, but I cannot use the power rule at this level. I can use it here, but I can't use it here. So now that I have this, I can find the derivative, and that is as simple as 2x plus 2. Got it? Thank you, William.
So you just simplify it down and that's it.
Basically, you have to simplify things down. Okay, so this was an example of how I would get around the product. Well, I have to show you how to get around a quotient as well. So let me give you an example of a quotient or a power. If I had something like this, E, F, G, H, I, J. Let's go to J. J of x. And it was 5 over 2x to the third.
2x to the third.
It's kind of a quotient. It's a little bit hard for me to find the derivative of it the way this is written. Okay? So I'm going to have to do something first before I can actually use the power rule. What I would do is we know the derivative of a constant, and we wrote this down earlier. We have a little rule that says that I know what the derivative of a constant is. The derivative of a constant is 0 when the constant is by itself. I also know that I can do the derivative of a constant times a variable will be, this constant will not affect anything. So I'm going to do this. I'm going to rewrite this as 5 halves times. Can I move that x to the third up? Is it the same thing as 5 halves times
Oh my gosh.
x to the negative third?
Yeah.
Exactly.
Okay. So there's a few other things that we will be using all the time. And since we're writing these rules right over here to the right-hand side, let me add these things here. We will use negative exponents, but we cannot leave our answers, no answers with negative exponents. We're not going to leave any answers with a negative exponent at all. There is something else that we'll use called the derivative of a constant multiple, d over dx of c times f of x is equal to c times f prime of x. Okay, so let me move that down just a little bit because I know it's easier to see right there. The derivative of a constant that's times by a function or f of x is equal to the constant times the derivative of f of x. You can actually take the derivative of just this piece and have it multiplied by the constant and you'll be okay. So this is what I'm going to use on this quotient rule. I'm going to take the derivative of just this piece here and then multiply it by this 5 halves. It won't affect my answer. So if I have j of x is equal to 5 halves times x to the negative third, I can now multiply this over here. And negative 3 times 5 halves, if I'm going to find j prime of x, I'm finding the derivative, would be negative 3 times 5 is negative 15 over 2. X to the negative 4, because I'm subtracting one from my exponent, right? Can I leave my answer like this? Nope. Is this my derivative? Yes, but it's not my final answer because Mr. Promo just told me no answers with negative exponents. We're not allowed to do that in calc. So we have to move this back down. So the derivative would be negative 15 over 2 x to the 4th. William gets excited when we do derivatives.
Wait, that's the answer?
That's the answer.
So it's basically the same exact thing as we were doing before, just in a different.
Yep.
Okay.
Wait, what?
One last example that I have to show you before we go to a different rule is what happens when you have a power. Let's go back to f of x. Let's say I had an f of x and it was the third root of x. The power rule, I have a variable, says that you have to use exponents. Well, this is in radical form. Good thing that in Algebra 2 we taught you how to switch things from radical form into exponential form.
Say what?
X to 1/3.
Thank you, William. This is x to the 1/3 power, isn't it? Do you remember where the bottom number is the bottom of the fraction and the power is the top part of the fraction? If you don't remember that, you are expected to know it, and you'll be using that as a part of this problem. There's a question. Okay.
No, I can't believe it.
Well, I'm still recording on this one, so I'm hoping that I still have memory on it. We'll just go with that. And so now if I want to find the derivative, I have to have it as an exponent. Now I have it as an exponent. I can use my power rule. I would multiply the 1, that this invisible 1 by the 1/3, and I get 1/3. The derivative is equal to 1/3 x. What happens when you subtract one whole exponent from a third of an exponent? What do you get?
Gets even smaller, just a negative.
Negative what?
Negative over third.
Thank you. If you are not good at subtracting fractions in your head, you should start, because you should not have to go to a calculator for that. Okay. So now we have this. Do I leave my answer with negative exponents?
No.
So my final answer would be 1/3. And I like to convert it back. You do not have to convert it back if you don't want to, but you can. 1/3 times the third root of x squared times the third root of x squared. You could either leave it like that or 1/3 times x to the 2/3 power. Either answer is correct. Robert.
Is the square inside the bracket or outside?
It actually can be either way. It's either in or out, doesn't matter. Any questions so far? Other questions? Helen.
Can you go back to the top and show me the other roll with us?
This one right here? The derivative with respect to x, d over dx, of a constant times a function times a variable is the constant times the derivative of f of x. Last two rules that we're going to do.
Oh god. Oh boy.
Boy, oh boy, oh boy.
What's the derivative of your best friend?
-3.
Sine of x.
Serious.
-3. Was that your best friend? Oh.
Oh, I see you have a best friend.
What's the derivative of cosine of x? Close. Okay, the derivative of sine of x is negative cosine of x.
That's not fair.
Sorry, positive, thank you.
Oh.
White out.
Nope.
I was doing two things at
That
once.
was awesome.
I was thinking about where I was going. The derivative of sine of x is cosine of x, and the derivative of cosine of x is
Sine.
negative sine of x. That's where the negative belongs.
Now you're confusing.
It's weird, isn't it?
Sort
I
of.
did not understand it until I looked at a picture in your textbook. So I'm going to show you the picture.
The pictures do help. Yeah.
Is it textbook?
This is the graph of sine of x. Quiet down. This is the graph of sine of x. If I look at the top at pi over 2, the sine is 0, right? So the slope of the tangent line is 0. Let's look at cosine's graph. At pi over 2, what's the value of pi over 2? 0. That's the same as the slope of the sine graph. Well, let's go here. The slope at pi for sine of x is -1. What's the value of cosine of x at pi? The value is -1. This is the slope of that graph, which means that the derivative of sine of x is the cosine of x.
Wow.
I really like this illustration. It's figure 2.18 in your textbook. It's on page 110 if you want to see it for yourself.
It's like magic.
For the same reasons, the derivative of cosine is a negative sine graph. These two things you will have to memorize. We are going to use them throughout these problems. Okay? If I asked you to find the derivative, look at how I'm writing it. Find the derivative of x plus cosine of x. Let's do this together. I want to find the derivative. That's what the d over dx means. What is the derivative with respect to x of x plus cosine x. Well, I have to take the derivative of the first piece. What's the derivative of x? Using the power rule. 1. And what's the derivative of a positive cosine of x, which we just memorized, hopefully?
Negative sine x.
So this is the derivative of x plus cosine x. Is 1 minus sine x.
Lols.
Pretty simple.
Maybe.
Last thing. Position.
Position. Position.
We're just ready to finish.
We tried to make Sarah laugh here. And she laughed right now.
If I have a function
And when she smiles.
the whole reason you are learning this, why on earth are we learning derivatives, Mr. Paramo? Because the derivative of position, okay, so let's call position S of t. Let's just do that. I'll put S of t right there. S of t equals position, okay? The derivative, stop crying, William. It sounds like you're crying. Okay. S of t is position. S prime of t, the derivative of position, is velocity.
Oh, that's not
Oh,
And you haven't learned this yet, but you will. The second derivative, which means the derivative of the derivative,
what?
is acceleration. Does calculus apply to the real world? Absolutely.
Makes sense though. Am I gonna play?
The derivative of position is velocity, and the second derivative is acceleration. So we need to know how to do that.
Directions.
Going low and low.
And physics.
You are going to have some questions. You're going to have some questions in your textbook that will ask you certain things. So let me give you one last example, and you'll be done. Let's say I have a diver.
Oh, God.
The diver's equation is negative 16 t squared plus 16t plus 32. Where S is measured in feet, S is in feet, and T is in seconds. T is in seconds.
Oh, there you go.
I was a little off the screen there, huh?
Yep.
At time t, a diver jumps from a platform diving board that is 32 feet above the water, hence the 32. The position of the diver is given by this. This is the position function. When does the diver hit the water? When does the diver hit the water? What is the diver's velocity at impact? So if I want to find the velocity, well, first off, we don't know when the diver hits the water. When the diver hits the water, what is the diver's position above the water? How high? When he hits the water, how high? What we would measure it as?
Zero?
Right.
Yeah,
Okay.
zero, baby.
So the very first question is when does he hit the water? When does he hit the water? Well, he'll do that when this value is equal to 0. So you are expected to be able to factor or solve this equation. Something like this, you would definitely, I would use a calculator if I were you. I would plug it in, I would solve it, and I would figure out where does it equal 0. I would find the zeros of the graphing calculator. So, to demonstrate that, I would plug it into my graphing calculator. You don't need to do so unless you feel like you want to. Negative 16 x squared plus 16x plus 32. I'm going to graph it and just see what it looks like. I'm getting a very, very tall, spiky parabola, right? The diver's position's way high, and I'm trying to figure out when this diver hits the water. It'll be right about there. Let me try to get the light just right. There we go. So I'm trying to calculate the 0. So I'm going to press calculate the 0 for me. And it's going to say, where's your left boundary line? Well, I want the left boundary line on the left side of this 0. And the right side there, and I want it to guess. And it tells me the 0 is at x is 2. So, time equals 0 is when, I'm sorry, I wrote that down incorrectly. Time is equal to 2 seconds. When h equals 0, right? Or the height, or s is equal to 0. Same thing. It's the height. What is the diver's velocity at impact?
Okay.
So now I need to find the velocity at impact. You could never do this in Algebra 2. Why couldn't you do it in Algebra 2? Because you didn't know what the derivative was. If the derivative of position is velocity. Now you know when the diver hits the water at 2 seconds. So we're going to need to know the velocity at impact. I need to know what the velocity is at 2 seconds. Well, how am I going to do that? I need to find the derivative of the position function, s prime of t. You can do that in your head, can't you? What's the derivative of negative 16t squared plus 16t plus 32? What's the derivative?
Negative 32t plus 16.
That's the derivative. This is the velocity function, the slope of the original graph. Same thing. This velocity, now if I want to know what the velocity is, what do? Plug in 2. Negative 32 times 2 plus 16. Negative 64 plus 16 is?
32. Negative 32.
Negative 48. Why is it negative? Is the diver going up or down?
Yeah.
So that's a reason why it's negative. And this is negative 48 feet per second. That's how fast the diver is traveling at that instance. That's the instantaneous velocity, not the average velocity. Instantaneous velocity.
So that's how fast he was doing it.
Yep.
So wait, that's supposed to be the answer right there?
Yep.
Of all that work you did.
No, there was 2 questions though.
Oh, okay.
When does he hit the water and what's the velocity at impact? This is the velocity at impact. You could also find the velocity after 1 second. There you go. We'll stop our recording right there.